capacitor consists in its simplest form of two parallel metal plates. In most cases, the two plates are kept separate by a piece of insulating material known as a dielectric, and the capacitor is rolled up to form a cylinder. Capacitors do not allow current to flow through them. Charge cannot pass from one plate to the other. However, charges can build up on the plates. Once the plates are full, no charge flows. Electronics in real life. Types of capacitor. Electronics in real life. Power supplies use very large capacitors, several thousand microfarads, to ensure that the voltage from them is constant or smooth. Generally speaking, the larger the capacitor in farads, the physically larger it will be. There is one type of capacitor that has a value much larger than its physical size suggests. Although they are no larger than a small torch battery, they can have a value of several thousand microfarads. This type of capacitor is called an electrolytic capacitor. You must be careful when using electrolytic capacitors. It's important to connect them the right way round in a circuit. They're marked to show which is the positive and which is the negative terminal. If you reverse the connection, they can explode. Electronics in... Consider the circuit shown here. The typical situation is that, at the start, no voltage appears across the capacitor. This means that when the switch is closed, all the battery voltage appears across the resistor, and current will flow. Because current cannot flow through the capacitor, charge will build up on the capacitor plates. This build-up of charge results in the voltage across the capacitor rising, leaving less of the battery voltage to appear across the resistor. From Ohm's law, I equals V divided by R, we know that if the voltage across the resistor decreases, the current will reduce and slow down the rate at which the capacitor charges. Click on the switch to close it and see how this affects the voltage around the circuit. Notice how the sum of the capacitor voltage and resistor voltage always equals the battery voltage. The battery used energy in charging up the capacitor. As well as storing charge, the capacitor stores energy. This energy is stored in the form of an electric field that exists in between the plates of the capacitor. The time taken to charge. The time taken for the capacitor to charge to a certain voltage depends on three things. 1. The battery voltage or EMF. 2. The size of the resistor. The bigger the resistor, the less current will flow and the longer the capacitor will take to charge. 3. The size of the capacitor. A large capacitor will need more charge to reach a given voltage and will therefore take longer to reach that voltage. If the value of the capacitor is C farads and the resistor value is R ohms, CR is known as the time constant. It even has the unit of seconds. The graph now has the timescale marked in increments of CR. To convert this to a graph with seconds as the timescale, you must calculate CR and replace it on the timescale with this value. As an example, suppose the capacitor has a value of 200 microfarads and the resistor has a value of 1000 ohms. Then C equals 0.0002 and R equals 1000. So CR equals 0.0002 times 1000 equals 0.2 seconds. The above graph could then be changed to that shown below. After a time period of 5 CR seconds, very little further change takes place. 5 CR is often referred to as the settling time of a circuit that contains resistors and capacitors. A graph is plotted to show the way in which the potential difference across a resistor in the circuit shown varies after the switch is closed. Click on the graph that shows the variation of resistor voltage. seconds is known as the settling time. Find the settling time in the circuit shown: A, when charging, S1 closed and S2 open, and B, when discharging, S1 open and S2 closed. An inductor consists of a tightly wound coil of wire, usually wound around a magnetic material such as soft iron. Inductors tend to smooth current flow in a similar way to that in which capacitors smooth voltage. Inductors also store energy, but in the form of a magnetic field. Inductance has the symbol L and is measured in henries. Its circuit symbol looks like this. Inductors and capacitors with AC voltages. Inductors and capacitors do not have resistance, but rather possess the property of reactance, which is measured in ohms. Reactance has the symbol X and is governed by the equation X equals V divided by I. Note the similarity with Ohm's equation, R equals V divided by I. Reactance only has real meaning when an AC voltage is applied across the inductor or capacitor. Suppose the frequency of the AC voltage is F, then the reactance of the capacitor, Xc, equals 1 divided by 2 pi Fc. The reactance of the inductor, Xl, equals 2 pi Fl.